Welcome to problem 3. Problem 3 is also a really interesting one, where you're given this induction problem. And basically, let's look at the hint first. So we want to compute Tn by direct enumerations. Well, n has to be greater than or equal to 3, so so we have T3, T2, and T1. And notice that we want to build a 2 by n set of tiles. So let's get started here. So if you have T1, where you have a 2 by 1, this is just tile B, right? So, and T2, this is 2 by 1. This is the 2 by 2 case. And now we have many possible combinations. We can have 2B, we can have 2A, and we can have the C. So 2B, 2A, or C. Now T3, how do you get from T1 to T3 and then T2 to T3? Well, notice from T1 to T3, you're missing, if I can draw this properly, you're missing a 2 by 2, so missing 2 by 2. And how do you fill this in? Well, you can, for instance, add a C, or you can add 2A. Now, why did I not include 2B? Well, you'll see in a moment. This is for T1 to T3. Now, for T2 to T3, you have some sort of setup here, and you're just missing a 2 by 1 piece. So, how can you fill this? You can only fill this with tile B. So, for every combo in T2, you add 1 because you add a tile B. And for every combo in T1, you add 2 different possibilities because 1 can come from C and 1 can come from 2A. So the reason why you need to not count 2B is because you already account for a B here. So then any other cases where you add B will be double counting from this spot. So, and this helps us a lot because we add 1 for each T2 and we add 2 for each T1. So we can guess the relation Tn equals to Tn minus 1 plus 2 Tn minus 2. And in general, this holds because we can forget about everything else we've built. We can forget about this. We just have to focus on the last 3 tiles where this can be not filled yet. So great. We've come up with this recurrence relation, and this will help us derive the following formula from induction. So let's get started on that. Recall, Tn equals to Tn minus 1 plus 2Tn minus 2. We need to prove the formula 2 to the n plus 1 plus negative 1 to the n over 3. So prove. And you guys are pretty much used to this by now. What we want to do is we want to have base cases. And notice, since we're going to use this recurrence relation and that it has 2 subproblems that it relies on and 2 landing spots, you need 2 base cases. So for n equals 1, we have 2 to the 1 plus 1 equals to 4 minus 3 over 3 equals to 1. 4 minus 1 over 3 equals to 1. And this corresponds to tile B. So this works. N equals 2, we have, so to make this clear, T1 equals to 1 and T2 equals to So for n equals 2, we have 2 plus 1 plus negative 1, 2 over 3 equals to 8 plus 1 over 3 equals to 3. And this matches our original recurrence relation, where you had 2b, 2c, and, c and 2a. Alright, so now the inductive hypothesis, of course, is to assume the formula is true for n. For 1 less than k less than n. Because we're going to have to go 2 at a time, so we need strong induction. Now, Tn plus 1, using the definition from our recurrence relation, equals to Tn plus 2 Tn minus 1. And from the inductive hypothesis, this is the inductive step, we have 2 to the 2 times 2 plus negative 1 n minus 1 over 3 plus 2 n plus 1 plus negative 1 n over 3. So I switched up the order a little bit. Sorry for the confusion. This is the Tn minus 1 case, and this is the Tn case. And so you can see that this simplifies to t to the 2n plus 1 plus 2 negative 1n minus 1 plus 2n plus 1 plus over 3. And then let me clear out this work here. So give you a second to paste. Alright, it's gone. Now, continuing on from our algebra, 2n plus 1 plus 2 negative 1n minus 1 plus 2n plus 1 plus negative 1n over 3. These two terms come together, so now you get 2n plus 1 plus 1. And we can factor out a negative 1n minus 1. This will give us 2 minus 1. So this is 2n plus 1. I'm leaving this here because we need to prove the inductive step. Plus negative 1n minus 1 over 3. Now notice that negative 1n minus 1, if you multiply that by 1, this 1 becomes negative 1 squared. And this actually is n plus 1. So negative 1 n minus 1 is equal to negative 1 of n plus 1 to the n plus 1 power. So we can actually replace this. And we've proven our inductive step. And therefore, we proved the equation that for part B that I didn't provide. Excellent. All right. That is it for this problem. Let's move on to problem 4.